Let's take a look at the initial value theorem, where we can find the initial value of the function in time domain at 0 plus by looking at the function in the frequency domain. So if we are doing a circuit working in the frequency domain, and we have the value of the function being a voltage or a current, if we multiply that current or voltage function by our complex frequency s, just the variable s, and we take the limit as s goes to infinity, that will give us the initial value in the time domain, of course at 0 plus. More properly written, we could say the limit as t approaches 0 plus of our function in time domain is equal to the limit as s approaches infinity of s times the function in the frequency domain. So we can derive that. How we derive it is from the our differentiation theorem. So the Laplace transform of df dt, the time domain derivative of our function, that we know is s times our function in the frequency domain minus our initial value at 0 minus as opposed to 0 plus. So that's our one-sided Laplace integral from 0 minus to infinity of e to the negative st df dt, that's the function, and then dt for our integral over time. We're going from time, t is equal to 0 minus, t is equal to infinity. So what we're showing here is if we take the limit as s goes to infinity of this function, f, our time derivative, our Laplace transform of the time derivative, that's the limit as s goes to infinity, then of this function here, right? We've used linearity to break up 0 minus to 0 plus and then 0 plus to infinity, because we want to look at from 0 plus to infinity, but our Laplace transform integral goes from 0 minus to infinity. So when we do that, we're just doing e to the power of 0 instead of e to the negative st, e to the 0 df dt dt. So that just gives us the integral of df. So that's going to give us f of 0 there, and then we have this portion of the function here. But if we look at this portion of the function, we're taking the limit as s goes to infinity, and as s goes to infinity, this term is just going to go to 0, as opposed to these two are when time is going from infinity to 0. So this whole term just goes to 0, and all we have here is the limit as s goes to infinity of our integral of 0 plus 0 minus, which is just f of 0 plus minus f of 0 minus. So that's what we get on the right hand side of our equation. Our left hand side of the equation, we're taking the limit as s goes to infinity. This is not a function of s. We pull that out, so we just take our limit as s goes to infinity of s times f of s. So that's minus our f of 0 minus. We have these then on both sides of the equation, and they're going to cancel. So they're going to cancel, and we've derived our initial value theorem from the time differentiation theorem. So we can evaluate the initial value of a function, our function at times t is equal to 0, by evaluating the function in the frequency domain. The advantage of this is we don't have to go back to time domain. We don't have to do our complete inverse Laplace transform to find that initial value, which might be all we want. So if we take a look at an example of that, check it. If we take our Laplace transform of our cosine, we'll do cosine omega naught t. Well, that's going to be, using our Laplace transform table, that's s over s squared plus omega naught squared. And we know the initial value of this, our cosine of 0, is 1. So let's take the limit of our function, multiply it by s, and take that limit as s goes to infinity, and that indeed is equal to 1. And we can show that, so this is just going to be, this becomes s squared. So if we multiply our numerator and denominator by s squared, which multiply both these terms by s squared, well, this is just going to go to 1. This is going to go to 1, and because s goes to infinity, this is going to go to 0. So we just end up with that equaling 1. So that's an example of how our initial value theorem works. In the next video, we'll look at the final value theorem.